All right, I'm going to do things slightly differently today. First of all, if you are seeing this before you take your exam 3, bear in mind nothing we're going to end up talking about in this video is going to show up on your exam. So this is all purely going to be on the final exam. It will be on the final, but it won't be on exam 3. And we're shifting gears a lot. And we'll also do a little bit different format here. Hopefully this will end up helping you to understand some stuff a little better. And the material we're covering on this one actually works for doing it this way. So I'm going to actually, for once, end up showing you some PowerPoint, and we'll end up seeing how that ends up going for you. So let me first pull this up, and then let's see. Here we go. Okay. What I want to do next, we'll look at that screen. Okay, so we're going to end up taking a look at atomic nuclei and how nuclear reactions take place. So in order to understand nuclear reactions, we need to end up understanding a few things about special relativity and quantum mechanics first. We don't have time to go into these in detail, but you'd have a few concepts you need to know. First thing is, from special relativity, mass is a kind of energy, and in particular, changes of mass will induce changes of energy. The amount of change of energy will equal the change in mass times the square of the speed of light. It's not obvious that this is true, but this is a fact from special relativity. In particular, this also means mass is not conserved. So if you learn mass is conserved in chemistry, well, it pretty close to is in chemistry, because the amounts of energy are and the mass is so much greater than the amount of energy and change in chemical reactions that we are literally unable to measure the difference in mass due to chemical reactions. The very best balances we have are just barely not quite good enough to do so. Then we have a few things from quantum mechanics you need to know. Vacuum, which is just empty space. It acts like an energy loan shark. You can borrow energy, unlike what you might have understood before. You can't get energy, but the more you borrow, the faster you have to pay it back, and you have to pay it back with kinetic energy interest. So the first one will end up being more important to us than the second. Next thing is quantum mechanics. Particles are like 3-year-olds. So if you end up having a 3-year-old that's in the back of a car, if it's a van, they're able to crawl around and do all kinds of stuff. Then they'll be active, but won't be quite so bad. You end up putting them in a car safety seat, and their hands are going to be wiggling around and going crazy, because the more confined they are, more confined a particle is, the higher the least kinetic energy can have. So again, that's totally different from what you have expected from classical mechanics. This is quantum mechanics. Some things where quantum mechanics and QM are combined. Identical fermions, and a fermion is a particle with a spin that's an odd multiple of 1/2. Identical fermions cannot be in the same state. This is Pauli exclusion principle you've heard of in chemistry. It's also true for protons and neutrons separately. So 2 protons cannot be in the same state. 2 neutrons cannot be in the same state, but you can have the same state occupied both by a proton and by a neutron. Next thing is electrons, and also particles that you may not be familiar with called electron neutrinos. Those are fermions. Photons aren't. We may or may not need to worry about that, but the fermion that you do need to know about the fermionic characteristics. And the second reason is fermions will also have corresponding particles. They have identical mass, but all their quantum numbers, which are the ones we're going to worry about, are charge, baryon number, and lepton number, which we'll get to in a minute. Those particles with the same mass but opposite quantum numbers are called antiparticles. The antiparticle to an electron is a positron. What happens whenever a particle and an antiparticle end up getting close to each other is that they will end up annihilating. So they end up turning in all of their mass energy from both particles will instantly turn into light. So, all right. Next thing you need to know is there are 3 big rules you need to know about, and there are no exceptions to any of these rules. First thing is conservation of electric charge. We've used Q for charge throughout the semester, but the standard symbol that we use in nuclear stuff is Z. So the electric charge we'll call Z. Next thing is conservation of baryon number. So matter baryons are comprised, I screwed that up. They're comprised of 3 matter quarks. So, and protons and neutrons are positive baryons. The 3 quarks that make them up are up, up, and down for a proton, up, down, and down for a neutron. The last of the 3 big rules, conservation of lepton number. Leptons are fermions that have no subparts. Electrons and electron neutrinos are examples of positive 1 leptons. Positrons, anti-electron, which are anti-electrons, and the electron antineutrino are negative leptons. There are no exceptions to these. So what we mean is if we start with however much charge, we have to end with that amount of charge. If we start with a number of baryons, we have to end with that number of baryons. If we start with a number of leptons, we have to end with that total number of leptons. So if you add a positive 1 and a negative 1, doesn't change it. So, but you can't end up changing the total number, including signs. Strong nuclear force is what ends up binding nuclei together. What keeps nuclei together are the force carriers called pions. And pions have a mass of about 135 million electron volts. By comparison, a proton is about 931 million electron volts. Neutrons about 932. Electrons just a little under half, just a little over 500,000, 511,000. In order to get a pion isn't free. The nucleon has to borrow the energy for the pion from the vacuum. But by the rule we set, if it has to borrow the energy from the vacuum, it can't go very far because it has to borrow a lot of mass. So and even at the speed of light, it just can't get very far. So that's the reason why nuclei are small. So the size of a nucleus is on the order of a femtometer. And by contrast with atoms, which you would be familiar with in chemistry, it's about 100,000 times smaller than a typical atom. The next thing about the strong nuclear force, why does it want to borrow pions, is because it gains a lot for that. The total force of attraction between each pair of nucleons is about 40 million electron volts from the ones that touch. However, it's also confined to a tight space from what we've said before. So that ends up meaning you get a lot of kinetic energy in these particles. So the total net effect, the drop in energy due to the binding force, then the necessary gain of kinetic energy to stay bound, will end up giving you a net, which is a lot smaller, but still is significant. It's about 3 to 8 million electron volts per nucleon. All right, next thing we need to do is to take a look at some symbols. A nucleus is a bound collection. It's got 1 or more protons and could have neutrons, could not. Protons and neutrons collectively are called nucleons. Symbol for a bare neutron is an N. So we don't call a bare neutron a nucleus. We just call it a particle N. A bare proton we can write as a P. We can also write it as H1 because it's the nucleus of a hydrogen 1 atom. And by the way, it will be helpful to you along the way to look at a periodic table of the elements sometimes along here so you can keep track of a few things that are going on. Electrons and positrons, we will write those as either a lowercase e or as a beta. And if we want to distinguish whether it's an electron or a positron, the electron will be an e with a minus sign to the upper right, or it will be written in somewhere else in terms of the charge to end up indicating that it's got a negative charge, and a positron will have a plus charge, either to the upper right of, so if it's beta plus to the plus to the upper right, that represents a positron, and so on. Photons are represented by a lowercase gamma, and electron neutrinos are represented by a lowercase Greek letter nu with a subscript e. An electron antineutrino is a lowercase nu with a subscript e with a bar on top. But all of these particles have no charge, and they are neither lepton, and that photons are neither leptons nor charged. Neutrinos have no charge, but they are leptons. Then for nuclear notation, I gave a typical example. This is a calcium 42. The number of protons determines the element symbol on the periodic table. So if on there, the baryon number in the upper left of the symbol is 42. That represents the total number of baryons in that nucleus. Because it's calcium, it's got an electric charge of plus 20. So there are 20 protons because each proton has a positive 1 charge. So the total number of neutrons, then you can calculate by taking 42 minus 20 to get 22 neutrons. Baryon number, you'll end up hearing it called, it is a standard term for it, it's called the mass number. But I do want you to understand that mass is not conserved in nuclear processes, but what is conserved is baryon number. So the baryon number is an exact whole number, whereas it's approximately equal to that many atomic mass units, but that it is that exact value as an integer of a baryon number. As I said, photons and neutrinos, whether matter or antimatter, there's no charge, so they're not baryons. So both the baryon number and the charge are 0 in terms of those symbols. Leptons are not baryons, but electrons and positrons do have a charge. So again, the number on the lower left, I don't want you to think, although it will be true for nuclei, that will be the atomic number. What it represents is the electric charge. So, so that is the reason why we can write electrons and positrons. And that's where the charge goes when we write a -1 to +1 on the lower left. Neutrons are baryons, so they have a +1 baryon number, but they have no charge. All right, nuclear structure. Protons and neutrons obey Pauli exclusion because they're fermions. They end up filling from the lowest possible energy, just like electrons do whenever you do the alpha structures in chemistry. Unlike chemistry, you have 2 distinct particles. So a proton and a neutron can have the same state because they're different kinds of fermions. So they are, so basically protons end up filling up their states completely independently of neutrons. Last thing about nuclear structure is that the binding forces between protons, neutrons and protons, neutrons and neutrons, they're all basically exactly the same. They're all about 40 million electron volts. So until you end up getting to the point electrostatic repulsion between protons is significant, the energy levels for protons and neutrons are almost exactly equal. One other thing, just like chemistry, there is a tendency to have pairing of fermions in nuclei. There are only 4 examples where you got a stable nucleus with an odd number of protons and neutrons, which are deuterium, lithium-6, boron-10, and nitrogen-14. There's also another one that has not yet been seen to decay, which is tantalum 180 metastable, but it's not the lowest energy species with this baryon number. So there is a nucleus that would be a tantalum 180 that has been synthesized. That has a half-life of a few minutes. This thing has never been seen to decay, and we'll talk more about why things are metastable in a little bit later. There are more stable nuclei with equal numbers of even numbers of neutrons and even number of protons than all the other possibilities combined. The last thing in terms of nuclear structure, so you have Phillips shells in chemistry. So you have the alkali, the noble gas structures that are filled shells in chemistry. You also have filled shells in nuclei, and so those have special stability. And the numbers of each, it's because protons and neutrons bind basically the same way. The magic numbers are the same for protons and for neutrons. So 2 protons is a magic number, 2 neutrons is a magic number, 8 neutrons is a magic number, 8 protons is a magic number, 20, 28, 50, 82, and 126 are the ones that are known. And this, if you're curious as to how we know exactly what those numbers are, there's a couple of things that you can end up seeing looking at just isotope tables. There are usually a larger number of isotopes that are stable that end up having that number of whichever one. It's also going to be true that if you end up trying to absorb new ones, so if you end up taking a neutron, for example, and you end up putting it toward one of them that's a magic number, the binding force is going to be significantly less. It will still bind, but binding force will be significantly less. So now let's talk about a nuclei that have a small charge. Basically up until calcium. So until your charge is 20, your lowest energy configuration will end up being where the number of protons and neutrons are nearly the same. Due to electrostatic repulsion, because you build up positive charges, glomming in another one, it will have some amount, still small enough that it doesn't affect the order of filling yet, but it's enough that if the charge is 2 or more, that it's more stable whenever you have an odd number of nucleons. It's more stable if the neutron count is the one that's higher than the proton count. For 3 nucleons, that's not enough to make a difference. Proton has a lower mass than a neutron plus an electron. So because of that, helium-3 is actually more stable than tritium is. But that is the oddball situation. Helium-4, it's got 2 neutrons and 2 protons. So it's a magic number of both. So that for that reason, whenever you end up having a heavy atom that wants to come apart some way, one of the easiest ways for it to come apart is to pinch off 2 protons and 2 neutrons together. And whenever that happens, what will end up splitting off is a helium-4, and we call it an alpha particle. So you can write it as a helium-4 if you want, but the symbol often used for it is just alpha, because that is so much more stable than anything else that you could end up breaking off that's small, that that one is basically just the little piece that will end up breaking off, as long as the whole thing doesn't blast itself apart, which we'll talk about a little later also. So whenever your nuclear charge is higher, then as you keep building on more and more protons, if you imagine doing that, then because they're positively charged, right? So they do repel. So eventually you get to the point where adding a proton is harder than adding a neutron starting with the same amount. So you end up building on larger numbers of neutrons than you do protons in the most stable configurations. So then in those conditions, whenever the charge is more than 20, that you'll always have for a stable species more neutrons in than you will protons. Moreover, if you get to very high charge, if you end up with bismuth or higher than bismuth, that there are no nuclei that are stable to decay, although some decay processes still may be very, very, very slow. The heaviest stable nucleus is lead-208, and part of the reason why that's stable is that it has simultaneously a magic number of protons of 82 and a magic number of neutrons, which is 126. So to describe what happens when nuclei interact and react with each other, we introduce a notation to end up keeping track of our conservation laws of baryon number and charge. Charge on a nucleus you can look up on your periodic table. So if you end up describing the problem, we normally don't, if we want to talk about a nucleus that has 6 protons and 6 neutrons, we won't say carbon 12 with 6 protons because carbon already has 6. So you can look up what the number is for the number of protons just from the periodic table. Notation for the long form of writing it is familiar from chemistry. You draw the same kind of yield sign that you would have seen in a chemistry reaction. It separates your reactants from your products. And so the total number of baryons, total charge, and the total lepton number before the arrow has to match the total number of each one of those on the right. To end up matching lepton numbers, at the end, basically balance everything else first. Then you take a look at where your lepton numbers are. If you end up needing to adjust the number, the way you do it is you add whichever electron neutrinos or electron antineutrinos in your products to balance it out. That neutrinos and antineutrinos have extremely small mass compared with all of the other particles that are involved. So there's no energetic issue about putting one in. So those are more or less totally free. So you don't have to work. So you work those in at the end. Well, let's take a look at an example. Suppose you hit a tritium. Let's take a tritium sheet at titanium 46, and you produce 2 alpha particles. So we want to figure out what the other species is. So we end up saying we've got 1 tritium plus, and so hydrogen you look up is atomic number 1. Titanium you look up is atomic number 22, so that's where those 2 numbers come from. So you end up putting those on the left. On the right-hand side, you've got 2 alpha particles. Notice the 2 that's written in front. So in order to end up keeping those in balance, one of the reasons I wrote this out was to end up helping to illustrate how you balance these whenever you do have a coefficient in front. So the total number of baryons is the number on the top. So the baryon number on the left side is the 3 from the tritium plus the 46 from the titanium. That will end up yielding then 2 alpha particles. Each one of them have 4. So you've got 2 times 4 accounted for in your alpha particles. Then whatever is left over, you do the arithmetic, and you find there are 41 left. As far as your total charge, that's the number on the bottom. So we have a positive 1 charge from the tritium, positive 22 from a titanium. That will end up yielding 2 alpha particles. Each one has +2, so that's where you got 2 times +2 there. You end up solving for that, and you end up finding 19. You look up on the periodic table, atomic number 19 is potassium. So you end up having what goes in the box is potassium 41. The final thing on this one, notice there weren't any leptons involved. There were no electrons produced or emitted. There were no beta particles. There were no positrons. There was none of that stuff. So if you don't have any leptons on the left, you don't have any on the right. You don't have to worry about it. So we'll end up looking at what electron capture is a little bit later. But for right now, Let's suppose that we have a beryllium-7 nucleus that absorbs an electron. You're given there's only one nucleus, so we want to write what that reaction will look like. So an electron has a -1 charge. It's not a baryon. So the symbol for an electron is 0 in the upper left, -1 on the lower left. And by the way, where these are offset, that's not standard. Just write them straight up against the symbol. The only reason they're offset is because it's a royal pain in the neck to try to end up making that shape come up in PowerPoint. So this was just writing it easier for me. So there's that offset there, ignore it. So the description then of the problem will be beryllium-4 plus an electron yields something. So to figure out what we get as one object, 7 plus 0 is 7 total baryons. On the bottom, we have +4 for the beryllium plus -1 charge for the electron, gives me a 3 charge. So atomic number of 3 is lithium. So we end up getting lithium-7. The left side, though, electrons are positive leptons. So we have one positive lepton on the right. So we have to have one positive lepton on the left. So we have to have one positive one on the right. And that a matter electron neutrino is a positive lepton. So we put a matter electron neutrino on the right, and both of them are zeros. So it doesn't end up changing either the baryon number or the charge number. And so that would end up giving you your final answer for that balanced reaction. Next thing we'll look at is writing these in a shorthand. And way to write a shorthand reaction, you end up putting one reactant, and then you have in parentheses, the first object will end up being effectively what you hit it with. There's a comma, and then one or more particles may come out inside the parentheses, and then you have another thing afterwards. So the objects that are in the parentheses before the comma are also a reactant. Excuse me. Whatever is in the parentheses after the comma is a product. So the symbol, so the shorthand notation I've got there is a deuterium, reacts with a helion, producing a proton and an alpha particle. This is a reaction that takes place in stars. So when we write it in that shorthand, you can expand it back out so that you can end up seeing what's going on for it to end up balancing it out. So that shows you the steps. And again, notice that was already balanced for you. It was 5, of course, total baryons on the left. So 1 plus 4 is 5 on the right. 3 positive charges on the left, so 3 positive charges on the right. So, and this one got screwed up in copying. So that should end up being a sulfur 36. So the 36 should be up on top. It gives you carbon 12 and 2 alpha particles. Wow, that looks bad. So 36, 16, and that got screwed up in the conversion. So that should be a 36 on the top for the sulfur, a 16 on the bottom, 12 on the top, 6 on the bottom for the carbon, the 2 alpha particles, 4 on top, 2 on the bottom. So if you end up setting that up, gives you 36 plus 12 is the total baryon number on the left. On the right, you've got 2 alpha particles, so that's 2 times 4. So you end up doing the arithmetic, and you find the total baryon number of what's on the blank will be 40. On the bottom row, sulfur is 16, carbon is 6, so you end up having a total of 22 on the left. You have 2 alpha particles on the right, 2 times 2 is 4, so you end up doing that, and I botched that pretty good. So that should end up being 18, so that ought to, instead of being calcium, that ought to be argon. So that ought to be an argon 40, so I ended up doing the quick algebra wrong. So fix that. Okay, nuclear decay. A list of nuclides is given on the top of page 456 in the textbook. So if you end up taking a look at those, most of the isotopes we know are not stable. On the farthest left of that, you end up having things that have very high numbers of protons relative to neutrons. There's a point at which there's no more that you can place on. So over there, if you end up sending over a proton, you fired at it in such a way that whenever it gets close, it just barely kisses the tip. It still will just bounce off. It just has no binding force at all to that. There's too much electrostatic repulsion. There's not a convenient low energy state for the proton to get into, so it'll just kick it off. When you have a nuclide like that that just cannot take any more protons, that will be on what's called the proton drip line. So if you end up having one, if it's on the drip line, protons will not adhere to it anymore. And there's also a maximum number of neutrons for a given number of protons. That's the neutron drip line. It's a little more complicated because neutrons don't have electrostatic repulsion, so it's only your just getting to too high an energy level to end up absorbing additional neutrons. It's also generally true that the neutron drip line will end up being increased by pairs. So if you put one neutron on, it may bounce off, but if you're able to put two on, it may still stick. So your neutron drip line is whenever, even if you can get a pair of them, the pair will not stick onto it. And it's a lot easier to end up moving protons the way you want because they are charged. So you can use an electric field. You end up increasing the speed. That's easy to make it go. You can bend the path easily with magnetic field. So you can end up directing charged particles pretty much whichever way you want. Neutrons are not charged, so it's much harder to be able to get neutrons to go where you want them to go. And for that reason, the oxygen drip line is known. The fluorine drip line even is not. So we know the drip line for 8 protons. We do not know it yet for 9. So none of the other neutron drip lines are actually known. But everything we're going to talk about the rest of the time will be inside the drip line. So we're not worried about just bare neutrons just flying off or bare protons flying off. If they end up wanting to they will try to get toward a more stable state in general. So there has to be some other process for it to end up getting there. The simplest one to understand is alpha particle emission. So in that situation, we talked about it before, a nucleus will end up rearranging. Remember, they've got a lot of kinetic energy in there. So whenever you end up seeing the picture in a book, of these little hard balls that are sitting there, and they're just sitting around, they're not doing anything. That's not how things work. They are really, really high speed, these particles that are inside there. So they're moving around a lot. So because they move around and they can wiggle and wobble and stuff, they can eventually, occasionally change the shape. Most nuclei in the ground state are pretty close to spherical. There's a little bit that on a few of them, a little bit oblong, but most of them are pretty close to being spherical in average shape. But whenever they wobble and wiggle and stuff, they can eventually get to a point where they would start to pinch off. And whenever they would start to pinch off in such a way that you can get 2 protons and 2 neutrons together, usually attached by a string of neutrons, that will end up being a way to be able to kick off an alpha particle. Now, whenever you have that particular configuration, normally the other neutrons will snap back to your original nucleus. We'll talk about what happens whenever you get one of them that wobbles and you get a bigger hump that ends up coming off a little bit later. But any of those, that type of nuclear decay even will require a really substantial distortion of the nuclear shape from normal, which is why all of these processes on a scale of the nuclear time scale is really short. So it takes a really long time. The nuclear time scale is about a octosecond or so, 10 to the negative 24th second. So even processes like whenever we talk about gamma decay of 10 to the negative 16th seconds, that still is about 100 million vibrations of a nucleus. So that still even is taking a while. For other processes that are macroscopic time, it's vast, vast multiples of your nuclear time scale for any of these things to happen. So it's very, very rare processes in one sense that end up taking place. But if you, but on a human time scale, you know, that still may not be a very long time, but relative to that time scale, all of these take a long time to happen. All right, the heavier the nuclide is, the higher the chance is that it will undergo alpha decay, because that's the decay process other than spontaneous fission, which we'll talk about later. It's the process that reduces the charge the most. So you end up getting rid of two positive charges, which if it's really, really, really high positive charge, so there's a lot of repulsion of the protons that are in there, that gets rid of a little bit of that tension. So it ends up being a process that ends up being easier to do. So thorium-232 will undergo alpha decay. And again, I don't know why this ended up, the superscripts went away, but thorium-232 will undergo alpha decay in its first step. So we want to figure out what the daughter nuclide is. So in order to do that, you start with a thorium-232. You look up on the periodic table. Thorium is atomic number 90. So you end up calculating what the total number of baryons on the left. You had 232, because in general with the decay process, there's either that electron captures the oddball most of the time, otherwise there's only one thing on the left. So you've got the 232 baryon number equals your alpha particle is 4, and what's left is 228. On the bottom, you have a positive 90 charge for a thorium. It loses 2 positive charges for the alpha particle, so you end up with 88 left, and 88 is atomic number for radon. So the daughter nuclide is radon 228, radium 228, excuse me. Okay, next type of decay are beta type. These are where you have either emission or absorption of electrons or positrons. Absorption of positron doesn't happen because they're not free particles around, but you can absorb electrons. We'll talk about that later. To understand what's going on, we have to end up understanding the composition of protons. We said that it was comprised of quarks. Proton is 2 up quarks. Each one of them have a positive 2/3 charge, and a down quark with a negative 1/3 charge. And a neutron is 1 up and 2 down, and you can check to see that those both give you the right total amount of charge. A proton is +1, neutron is 0. Beta decay will happen whenever an interaction will cause an interchange between something that was an up quark, turns it into a down quark. In order to do that, it ends up requiring the weak nuclear force. And the weak nuclear force involves the W bosons. And they are really, really heavy. 80.4 billion electron volts. Again, by comparison, a proton and a neutron themselves are less than 1 billion. So this is a tremendously heavy particle that has to end up borrowing from the vacuum. And the fact that it has to borrow so much energy to make this process take place is the reason beta decays can end up being very slow processes. So that's the reason why the decay rate can be very, very slow. So there are single beta decay things that can end up taking billions of years on the average. A negative beta decay will end up being where you have a down quark that would be inside of a neutron. it will end up temporarily, that down quark will spit out and borrow the energy to spit out a W particle. So it turns it into an up quark. And then the negative W particle rapidly turns into an electron and anti-neutrino. The electron has a positive one, baryon has positive one lepton number, anti-neutrino has a negative one. So again, start with 0, you end with 0. And so this converts the neutron into a proton. However, again, we talked about before that you can borrow energy, but it has to pay for itself in kinetic energy interest. So these particles have to have kinetic energy to leave the nucleus whenever that happens. If they don't, then the whole process will not happen. So you can't borrow and owe energy to the vacuum. It just won't let you do it. A regular positive beta decay is the inverse, basically. So an up quark will end up absorbing enough energy to temporarily emit a positive W particle to become down, and then the positive W particle becomes a positron, which is a negative lepton, and an electron neutrino, which is a positive one lepton number. And we normally don't write the W step because that's happening sort of internal to it. So that's not something we can actually externally detect in this process. So we don't write down the intermediate step in any of these cases that involve your W boson. There's another beta type decay called electron capture. In this situation, an electron, which is effectively always 1s electron, because that's the one, because it's the closest electron to the nucleus, so it has the most overlap with the interior of the nucleus. Now, there's also, even a really, really high charge nucleus will not have the 1s electron in there very often, but it will end up being inside sometimes. And in this situation, the other thing mentally that you get with those pictures in textbooks of these hard little balls that make up the protons and neutrons, that you end up mentally thinking, okay, they're solid, so things can't get inside. There's no rule whatever that prevents interpenetration. So electrons can physically get inside the nucleus. It's just really small, so it's really unlikely, but it can sometimes happen. In this scenario, when you have electron capture, the electron ends up coming in interaction to end up borrowing enough energy to become a negative W particle in an electron neutrino. And then that negative W is absorbed by an up quark to end up converting it into a neutron. Again, when we always ignore the W particle when we write the overall reaction because it's borrowed and then it's paid back. And so there's never a net W particle that's involved. The most actually that this is not, there are examples of double electron captures as well. So you have regular double beta decay or a regular double electron capture. But in either case, the nucleus ends up borrowing 2 W bosons instead of 1. So it takes twice as much energy to be able to do that. Because that's the case, then your really, really fast double beta decay reactions are ones with half-lives of 100 quintillion years. So these are very, very, very slow just because you have to borrow such an extreme amount of energy to be able to make them happen. And so it's, we'll take a look at some examples of beta decays. The last step in a breeder reaction will be beta decay of neptunium-239. We'll find the daughter nuclide whenever there's no positive or negative. When I say beta decay, you can assume it's negative beta decay. So it's kicking out an electron. Now, again, I do want to make sure, because there's something else that we'll see a little later that involves electrons that actually are there. This is an electron that did not exist before. So this is a brand new electron that's produced whenever we have beta decay. It's not a 1s electron in the atom. It's not an electron that was in the atom at all. It's produced inside the nucleus. So in this situation, we've got a Neptunium-239. It ends up kicking out an electron. So we already know what that notation is. So we end up adding these together. Like before, the total baryon number has to match. So we have 239 on the left, so we've got to have 239 on the right. We have a positive 93 charge on the left. We end up losing a -1 charge, so we have 94 positive charges left. So that's how we get plutonium-239. There's also in this process an electron antineutrino produced, and in terms of understanding why, we end up producing a positive. And remember, it can be confusing. An electron is a matter particle, so it's a matter lepton, which means it's a positive amount of leptons. So it's a positive lepton. So we have to have an antineutrino to end up causing that to be balanced to 0. Positron emission tomography ends up using various nuclides, but the longest lived one, so it's the one that's the most commonly used, is fluorine-18. So that will undergo positron emission to end up seeing what that process is. We end up taking our fluorine-18, and then it will end up kicking out a positron. So a positron has a +1 charge. So we end up doing the arithmetic. We get an oxygen-18 is what's produced. And because a positron is an antimatter lepton, it's a negative lepton, so we need a matter neutrino, which will end up being an electron neutrino without the bar, is what we end up getting as the second piece. Electron capture, mercury-197 will undergo electron capture. To get that reaction, that's the one where we do have an electron on the left, because the nucleus in electron capture does absorb a real physical electron that's buzzing around the atom in that process. So that is gained by the nucleus. So in terms of the nucleus, we have our mercury-197. So we have 197 baryon number on the left, so we have 197 total on the right. 80 plus, we add a negative charge from the electron, we end up with a total of 79 on the left. So we end up with 79 charge on the right, which is gold. And then what's left over, because on the left side, we have a positive amount of lepton, we have a positive electron neutrino on the right. Then sulfur-38 undergoes double beta decay. So to see how that works, you'll take your sulfur-38 on the left, then you have 2 beta particles on the right, and so what you end up with is then argon-38 on the right, just doing the arithmetic, and that since you produce 2 positive leptons, you have 2 negative leptons you have to add to it, so that's where you get your 2 electron antineutrinos from. Next type of decay is called a gamma type decay. Whenever you have an atom that's in an excited state, it will end up emitting light because your transitions involve electromagnetic interactions, so you can end up producing electromagnetic radiation. So when you talk about atomic spectra, that's where this comes from. So a nucleus in an excited state can end up doing several things depending on how much excess energy. But if the excess energy is on that scale fairly small, typically if it's less than 1 million electron volts, it pretty much always will just end up emitting doing gamma type decay. If it's more than that, it still might, but other processes like alpha decay or something like that may end up happening instead. But if it's small enough, it will emit light, and light that's emitted from a nucleus undergoing an electric transition is called gamma ray. And typical period for a gamma decay is on the order of tenths of femtoseconds or so. So it is very, very short on a human time scale, but it still takes a while on the scale of nuclear oscillations. It's still, on the order of 100 million uh, nuclear wiggles before you end up getting your gamma decay. Excuse me. Uh, light gamma rays will have a spin of 1. So if your initial and final state are different by a spin of 1, you get very rapid decay. So that's your 10 to the negative 16th seconds. If they're different by more, the greater the difference, the slower the emission will be. If the difference is 4-ish or more, the excited state, if there's not an intermediate one where they can go to as well. If all of those are the case, the excited state may last for a while, and we end up calling states where that last for a while, although they're not the lowest possible energy state for that baryon number and nuclear charge. They're called metastable states, and so you end up putting an M beside the baryon number. If there's more than one metastable state, then you'll end up seeing, M1 or M2 or whatever like that to end up distinguishing them. And in general, the higher the number on the M, the higher the energy is. So an important weird case is tantalum 180 metastable. It would have to go down by 10 to go to a lower energy state. So that has a half-life that is at least a quintillion years. It's never been seen to decay. So, I mean, it's not a very common isotope. It's a pretty low percentage, so it's a little hard to be able to get to, but we've never seen it decay at all. That's just because that's so rare to be able to spin that much much gain of spin by a light particle. Different thing that can happen. It will lower the energy in a nucleus without changing its baryon or atomic number. The internal conversion. And what happens there is an electron that's in your 1s orbital will absorb nucleus energy and then get kicked out of the atom. So, because the amount of energy is drastically more than the binding energy of a 1s electron. So it will kick out the electron, but it is important to understand internal conversion is different from beta decay. In internal conversion, the electron was already there. It was part of an atom or an ion that was there prior to the internal conversion. So it just kicks out an electron that was already present. After an internal conversion, then you end up having a low energy vacancy in your electron structure. So what will happen is a high energy electron will end up dropping down into that state, and because it can't go through an intermediate because of Pauli exclusion, all the energy is dropped in one fell swoop. And that energy change is emitted as radiation, which is called an X-ray. So whenever you have internal conversions that end up going on, you end up getting X-rays. It is important to recognize the difference, what the difference between an X-ray and a gamma ray is. It's not even necessarily the amount of energy, it's where does the energy come from. An X-ray is an electronic transition of electrons in an atom going from a valence level state down to the 1s orbital. So that's distinct from what happens with a gamma ray, where this is changing the electron, changing the configuration inside of the nucleus. It has nothing to do with the electrons outside the nucleus at all. Last type of nuclear decay is a pretty oddball one, although it's not necessarily super rare. It's stochastic. So the other ones, when we have alpha decay, we know what's going to be produced. It's got 2 protons, 2 neutrons. If it is a positron decay, it will lose a positron. So we know what will happen whenever you have one of these. Spontaneous fission, what happens is you have this, again, roiling, wiggling mass of charge and neutrons that wiggles around and will end up changing its shape over time. And in spontaneous fission, what happens, you'll end up getting randomly a glob that will end up being momentarily separated from the rest of it by a chain of neutrons. And in this situation, that the electric repulsion between the two smaller globs can end up causing it to fly apart. When that happens, those neutrons that are holding the two bits together are now released. They're not attached to anything anymore. So you'll end up getting two smaller random globs of protons and neutrons, which are now new nuclei that are produced from it. But because of this randomness, that you can't predict which things will form. In fact, if you have spontaneous fission with identical things that you start with, it's typical that you're going to end up having as many as a difference of 10 total charges. So you have that about roughly 60% will end up on one, but it is rough. It can be more, it can be less. And roughly 40% will be the other one. Again, that's just by the random way it will end up coming apart. So it's unlikely for it to be symmetric because it's just random wiggling. So it's easier to pinch off something a little bit smaller. So that's why you end up with that where it's about 40, 60. And once you do have a spontaneous fission, the daughters will have smaller amounts of proton charges. So they don't need as many neutrons as the heavier one did in order to be stable. So typically those will end up being highly radioactive and do a lot of beta decays to end up converting some of those excess neutrons into protons to get closer to stability. In the next lecture we'll end up talking about nuclear kinetics, and we will hopefully also talk a little bit about the structure of stars. Those are probably not going to end up being, I probably won't do those on PowerPoint, but this one, like I said, lends itself pretty well to a PowerPoint, which is why I did it that way.